Okay, so the last few lectures we have been discussing about the different configurations. So in the discussions we have seen that there are three configurations which are possible in a BJT. These are common base, common emitter, and common collector. Also, while discussions we have seen that any of these configurations can be biased to work in either of the three regions, namely cutoff region of operation, saturation region of operation, and active region of operation. So any of these regions can be actually used here for these three configurations CB, CE, and CC. We have also seen that in the cutoff region there is actually no current, only the leakage current is possible. In saturation current, both the junctions are forward biased and a huge amount of current flows. We don't have any control on that. Uh, and in the most of the characteristics, we have seen that the output characteristic, if we look at, which is important for us. So in the output characteristic, we draw the characteristic between the output current IC and output voltage. Some having the terminal uh, collector, I think. So depending on the uh, configurations, we may have BCB here or BCE here or some some voltage like this. Okay, so it could be BCE or it could be BCB. So we have seen that in the saturation say we take say BCB here, sorry, this as a common base configuration, then we have seen that in the common base configuration, the input is given at a emitter and output is taken at collector. So emitter current is varied. Okay, so for different emitter currents, we can think of changing the BCB and getting the IC. So for a particular value of IE, say it was 0, say IE is equal to 0, we have some leakage current, and below this we have designated as this cutoff region. Any value above 0 for IE gives a different curve, like here. So this is say IE, which is non-zero, I have different value. So for this, so in this here, we see that there is a region on this side for a small value of BCB, for which our both junctions are forward biased, and gives this is what the saturation region be called. Okay, this is the saturation region, and between the saturation region and the cutoff region we have the active region. Okay, so this full region here, this full region, this is called active region. In the active region also, in the last lecture we saw that we cannot randomly increase the BCB to a large value, and in order to have and also we cannot increase the IE to a large value. because there is something called as power dissipation also happens. Okay, so if the power dissipation is large enough in the device, then it can break down. Okay, so we have also seen such a curve, something like this. If IC is more BCB or BC is kept smaller, so that the power dissipation, which is say output voltage B and output current I. Okay, we are not putting suffixes here. It could be BCB kind of thing and IC, or BC into IC kind of things. Okay, so there is a maximum rating of this, which should not exceed. Okay, so it happens that below this curve we will have a region like this here, which is only useful in saturation region. If we change some signal, then we can see that the level of current are saturated. So if we change the input values, then output, in the output we will not see the similar values here. Okay, so uh, that is not actually useful for us. Similarly, in the cutoff region, if we bias and change the input signal to a little a small value, one part goes into the active region, another part will go into the cutoff region. Okay, that is also not useful. Okay, in the cutoff region, the output is not proportional to the input. Okay, so input may be changing, but we will be not getting any output corresponding to that. So these are the problems. Okay, associated with these different regions of operations. So basically, saturation region and cutoff region, these are useful for the uh, say switching purpose. Okay, to make some circuit on or off, whereas it is only the active region which is useful, and also below the PC max. Okay, so this yellow curve which we see, this is called as PC max. Okay, so below this we have to keep ourselves. So we can see that there is a limited, the active region is actually uh, covered from all sides here. In one side from saturation region, and from other side it is from cutoff region, and from the third side it is from PC max. Okay, so if we violate the PC max, then our power dissipations will may be too large, which may raise the temperature of the device. Okay, and may ultimately lead into the breakdown regions. So we in order to make the transistor and its particular configurations useful, we do something called as biasing. Okay, so we apply some DC voltages to a transistor in order to turn it on so that it can amplify AC signals. So the amplification of the signals which we are claiming here, this is obtained in the active region. So that we will understand, try to understand in more detail. So in the active region, as already we have advocated that base emitter junction is forward biased and base collector junction is reverse biased. So, and also below we can see the cutoff regions and saturation regions operations defined. So DC biasing circuits we actually use to avoid the use of two independent voltage sources. Okay, voltage sources are very bulky and costlier, so we don't want to use multiple by voltage sources. Okay, in the discussions we have seen, suppose we take the common base configuration here, then base emitter junction was forward biased with the help of a voltage source like this, and the collector base junction, this was reverse biased by the use of a voltage source like this. Okay, so these voltages we can see here that how we can apply here. This is basically PNP transistor. Okay, so in the PNP transistor we have these two diodes at these two corresponding to these two junctions here. Okay, emitter junction and collector junction. So corresponding to these, we have these two diodes like appearance here, and basically we are forward biasing and are reverse biasing these diodes. So to forward bias this particular diode, we apply this kind of voltage source, and to say reverse bias this diode here, we apply this kind of voltage. So positive polarity is applied towards the P side, and positive polarity is here applied to the N side. Okay, so that is what we mean by forward bias and reverse bias. So to avoid these two independent voltage sources, we need now two voltage sources. Okay, but because of the set regions here, we want to avoid these, so we use some specialized circuits. These are called biasing circuits. So we will now try to understand what are the different types of biasing circuits and how to analyze how to use them, and how to analyze a circuit using these biasing circuits. So typically we have here four types of biasing circuits which we will study over here, but it is not limited to only these. Be it when you use a particular biasing circuit, they have their some advantages, and sometimes they also have some disadvantages. Okay. So depending on the application, we can choose a particular types of biasing circuit, and also sometimes some modifications are done in these biasing circuits to uh, cater some different characteristics here. So we will take one by one of these biasing circuits here and try to understand what we mean here. So the very first biasing circuit is here, which we are trying to take is fixed bias circuit. The fixed bias circuit, the main circuit is actually this one. We should look at this part first. There are some capacitors C1 and C2 are connected here at the input and output. We will shall discuss in a little later. Here, if we look at this circuit here, then it is essentially using a single BCC. There is a resistance RB, RC, and using these RB and RC, we generate voltages which appear across emitter junction and collector junction, such that emitter junction becomes forward biased and collector junction becomes reverse biased. Okay. Now let us see for what purpose actually we are using this C1 and C1 and C2. So C1 is used, C1 and C2, okay, these are by name called coupling capacitors. The name is not obvious right now, but will be obvious when we understand what we mean here. The very basic characteristic of a capacitor is like this here. We have a capacitor. If we apply some signal, okay, of frequency, where say omega radian per second, this is say frequency of the signal applied, then we see that the amount of impedance, say Xc, offered by this capacitor, we can write here as 1 upon j omega c. Okay, where omega is 2 pi f actually. Okay. F is the frequency in radian, sorry, in hertz, whereas omega is in radian per second. Okay, so we can see in this expression here that omega is coming in the denominator here. So as omega increases, then Xc decreases, and vice versa. If omega decreases, then Xc increases. Okay. So for a DC signal, if we look at a DC signal applied across C1, across capacitor C, then omega is going to be 0 for a DC signal, and Xc will be infinite. On the other hand, if we have omega is equal to very large, then Xc will be very less. So this is equivalent to a short circuit case, and the first one is like an open circuit. Okay, so open circuit and short circuit. So actually when we apply the AC signals, wiring signals, then there is not much problem in passing through these capacitors, these signals, because they act like a short circuit. And because of this reason, this is called as coupling capacitor. So AC components passes through the capacitors, whereas if we apply a DC signal across a capacitor, then it is not going to pass through it because it is going to act like an open circuit. Okay. So for DC signals, DC signals are being blocked here. So we can also call as DC blocking element. Okay, the capacitor is as a DC blocking element, whereas the capacitor is passing the AC signals through it. Okay, so for AC signals, this is going to appear as if it is not present, or if it is present, then it is offering a very small resistance. The path. So the on the other advantage of capacitors C1 and C2 being used are like this, that the effect of this BCC, which one is using over here to apply some biasing voltage across the emitter junction and collector junctions, they do not interfere. The value of BCC do not interfere with the AC signal DC values, okay, or the output signal DC values, because they are being blocked here. So the effect of BCC is only within the regime of C1 and C2. Okay, outside they do not affect the either input signal DC values or AC output signal values at the output. So C1 and C2 are used for these purpose. So fixed bias circuit, let us look at how this BCC is able to generate the voltage required to forward bias the emitter junction and reverse bias the collector junction, and how to analyze this particular circuit. So very first thing which we can do is use something called as load line. So load line actually we will discuss here first. So just we have actually when we try to analyze the biasing circuit, we take only the part of the circuit which is within the time of the capacitor C1 and C2. This is our transistor. Let us say that this is resistance RC and this is resistance RB, voltage source BCC. This particular transistor, we can first look at that in which configuration we are using it here. This is an example. In different ways also we can use the transistors in different configurations, I mean. Here we have just removed that output was being taken here at the collector and input was being given at the base. Okay, so and emitter is just grounded, the difference is taken. Okay, all other different terminals voltages are being measured with respect to the emitter voltages. Okay, emitter terminal. So emitter happens to be a common terminal. Okay, so emitter is common here, so it is obvious here that this is common emitter configuration. Okay, so this is common emitter configuration here. So in this, the emitter junction and collector junction we can assign here like this. And moreover, what we can see, because of the kind of arrow in the emitter leg, we can readily say that this is NPN transistor. Okay, so NPN transistor is being used in the common emitter configuration. We can also see the cross-sectional views of here, just for illustration purpose, that NPN transistor is like this here, and we are giving the input at base, emitter is common, and we are taking the output as collector here. So our collector junction is above 1 and the emitter junction is below 1. So we need to apply some voltages here. So for forward bias, we need this kind of voltage here across this emitter junction, and for reverse bias this, we need a voltage with a higher potential on the N side and lower potential on the P side, something like this. So let us see whether we are able to generate this kind of voltages across this or not. RB, which we are using, RB is actually used have a large value. Large value, why large value? Because the in the transistor we have seen that IB current is small. We cannot make the IB too large. So IB is small means we need to apply a large resistance RB. Okay. So RB voltage is large enough. Similarly, RC is not that much large as RB because we need a positive voltage on the collector side at collector here as compared to the base. Okay, this voltage which we call as BCB. So BCB has to have this kind of polarity. So this should be as less positive and this should be more positive. Then only we will have a voltage across this. So this is just qualitative views. For a now let us look at how we can analyze it. Suppose we are given some typical values of RB, RC. The transistor is known to us, say BCC values are known to us here. Let us see. Uh, also, let us assume that the voltage are such that the base emitter junction is forward biased and collector base junction is reverse biased. So let us say that these are given to us and we are asked to analyze this circuit for the collector current and all other voltages like base voltage, emitter voltage, collector voltage. Emitter voltage need not be calculated because it is grounded, so B is equal to 0. So when we have the knowledge of the transistor, we mean here that we know about the characteristics of this. So because this is common emitter configuration, so the characteristic of this which is known to us will be between IC and BCE for different values of IB. So IB will be changed here. So IB for IB 0, we will have a particular curve here, and for say higher value of IB, we will have some other curve like this. So a family of curves we have here. So for IB1, IB2, IB3, we have a family of curves here like this. So this is known to us. Now, first we have seen in the previous slide in the PPT that there is something called as load line analysis. So let us try to look at what we mean by load line here. We have already actually discussed about the diode circuits, diode characteristics, and we introduced there some the concept of the load line. Similar to here, we have actually in the transistor three legs: base, emitter, and collector. One is we have seen that based on different configurations here, we have input and output also. So for the load line, we choose the part of this transistor circuit which lies in the output. So in the output parts, if we look at here, then it is the, let me draw it again here quickly. So RC, RB, emitter, base, collector. So in the output side, this is output side and this is input side here. We applied input at base and we take the output at collector. So at the output side here we have this path. BCC here, it means here that we are applying a voltage source of which positive polarity is facing this node here and negative polarity is being grounded. The emitter here also is grounded here. So we can say that this is something like this, that these are connected together. So actually what we see that in reality this is forming a loop here. A kind of loop is being formed here, which we call as output loop here. So once we see this output loop, we can write a corresponding value of the KVL, Kirchhoff's voltage law, in this loop. Okay, it is connected. Let us assume that a current IC is flowing into this loop. The direction of the current, we can see that it is in this direction, because we can see that this is NPN transistor. So the current is flowing like this here through emitter and collector, and the through base, something like this. So transistor equation, if we do, if we write here IE, IC, IB, then it is like this: IB plus IC is equal to IE. This kind of equation we can write here in a transistor. So in a simple circuit and a transistor circuit, the difference is that this is a three-terminal device, and we need to write the equations separately for the input and output ports. Okay, input side and output side. And we should not forget about the different current which flows through different terminals there. Okay, just like here we see that through RC current IC is flowing, whereas through emitter terminal the current I is flowing. Whereas if we see in at the input side, then it will be the base current which is going to flow, IB. Okay, so these are the differences. Yet we have to note down all these currents, which current flow through which terminal. So once we are able to find it out what currents are flowing, we are now ready to write the KVL. So while writing the KVL, we know that we can start from any direction here. So if we encounter say negative first here in going from one side to other side, then we will write negative sign first. So minus BCC, and current is flowing like this. So the voltage drop across RC will be with this polarity, and the value of the voltage drop will be IC times RC. And let us say that between collector and emitter there is a voltage drop equal to BCE. So BCE can also be written like this here, equal to 0. So this is the kind of KVL we can write at the output, and this we can write the BCE to be equal to BCC minus IC times RC. Okay, so this is the KVL at the output loop. In this here, if if we make IC to be equal to 0, then BCE will be equal to just BCC. Okay, and if BCE is equal to 0, then IC will be equal to BCC upon RC. Okay, so these two values are very important here. The characteristic which we have drawn for the common emitter is between IC and BCE. And we wrote the KVL equation corresponding to the output, which is here BCE is equal to BCC minus IC RC. Now we took the two extreme points of this equation, this equation, okay, this equation is actually written for the output port, okay, which is having the RC. RC is also called as load. So the extent of this output KBL, which consists of this load, we call this as a load line, because we can see that this equation is looks like an equation of line, and this comprises of this load of this circuit here, RC. So for this reason, this is also called as load line. So to draw this load line, we take two extreme points. One is IC is equal to 0, okay, and another is BC is equal to 0. So when BC is equal to 0, we have the maximum current BCC upon RC. So BCC upon RC we can calculate here for a value of supply voltage BCC and load value RC. This current is a fixed value. Similarly, if IC is equal to 0, then BCE is equal to BCC. So BCE is the output voltage, okay. At collector, we have just seen that the voltage at output node is at collector. The voltage measured at collector with respect to the emitter, that is ground, is BCE. So maximum output voltage which we get is BCC here. So some point here we will have BCC, Now if we connect these two extreme points, then we have an equation of line here. This is nothing but called as load line. Now, depending on the input circuitry, we will have some base current IB. So we have to draw that characteristic here corresponding to that base current IB, and the intersection point of these two curves. This gives the solution of the particular value of voltage at the output and particular voltage current at the output. So IC and BCE, we get some particular value of this. This point of operation is called as Q point, and the corresponding values of the current are called as ICQ and BCEQ. So we get a corresponding value of the current and voltage. But this graphical method is difficult in the sense that we need to have family of curves here for a given transistor. So we have to do experimentation and we can find out that. Another thing is that we know some parameters of these transistors which we have understood a little in the previous few lectures. The parameters like large signal gain, alpha or beta. Alpha was for common base and beta was for the common emitter configuration. Okay, so either of these if we know, then most of the things can be calculated using the transistor equations, and we don't need actually the family of curves for that. So these alpha or beta are going to be very important for us. So this was the graphical method here. Now let us let us try to do the uh, equation based calculations for the same circuit here. So again let us redraw the circuit here. So BCC, RC, RB. Suppose the beta factor is known to us. Beta factor of this is known to us because this is in the common emitter configuration. BCC, already we have said that when we are given like this here, it means we have this kind of configuration. So same value BCC is being applied at across RC as well as across RB here. So we can actually understand this equation, this circuitry as if we are having RB here, RC, okay. So we can visualize this circuit as if it is like this. So transistor is there, and BCC is applied at RB and RC both. So it is not necessary to always redraw. Okay, so it is not. It is just for illustration purpose. So from here we can actually see clearly now two loops. One, the input loop and output loop. The voltage across collector emitter is BCE, and the voltage across base emitter is BBE. Let us say the current through RC we have assumed IC, and through resistance RB we will have current IB. Now we can write the equations here for the say input circuit. Our for output circuit already we have written. It is the same. It will be same equation. But for input, let us write now. So the current is going to flow in this direction here. We will make a voltage drop across RV with this polarity here, and the base emitter voltage will be in this polarity. So minus BCC plus IB times RB plus BBE will be equal to 0. If we write the KVL for the input loop, from here one can write IB to be equal to BCC minus BBE upon RB. So this is the equation for the current IB. Now depending on the required value of IB at the base, we can uh, design our value of RB. Okay. BBE, if we look at this BBE value, BBE is mostly fixed value. Okay. Already in a tabular form, in the some of the lecture we have seen that for silicon in the active region, the BBE is around 0.7 or 0.8 volt. Okay. So sometimes it is taken at 0.7, and sometimes it may be taken as 0.8 as stated. If not stated, then we can take it 0.7. In saturation, I think we have seen that it is uh, 0.8, and in active region it is 0.7. Okay, so it will be stated. We can find out that from there. And BCC is applied externally, so we will be knowing about this, and depending on that, to which uh, to which value of IB we want to generate the curve, okay, RB are corresponding, we can choose the value of RB. Our RB is given, say, and then we can find out the IB. So once we know IB, from the knowledge of IB, we can find out the IC. How we can find out the IC? We have learned that IC is equal to almost beta times IB in the common emitter configuration. So using this equation, one can also use this beta times IB. And once one knows this value of IC, one can find out this BCE. How one can find out the BCE? The equation for BCE is written over here. Okay, so BCE equation is here. So BCC minus IC into RC. So IC is known to us. Once it is known to us, RC is already given. So BCE can be found. Okay. So BCE is now known to us. Okay. So what we found? We found IB. From IB, we found IC. And from here, we found BCE. We have already uh, fixed the BBE to say 0.7 volt to make the transistor operate in the active region. So base voltage one can find out to be 0.7 volt. Emitter voltage is 0 because emitter is uh, grounded here. So BCE can be written as BC minus BE, and from here one can find out BC to be equal to just BCE. The BCE value which was calculated here, the same value is coming over here. So all the values are known to us now. Okay, so base voltage, emitter voltage, collector voltage, IC current, IB current, everything is now known to us. Okay, so this is the goal of finding out and doing this analysis. Okay, from this analysis we can find out all these parameters of the transistors and circuits. Okay, so with this we stop here. We try to first look at this fixed bias circuit today, and other circuit topologies we will look at in the coming lectures. Now based on that today's discussion, you can solve some of the problems from the books. Okay, so you can find out a lot many questions in the Bollisted book. So Bollisted book okay, so you can just note down the book here, Electronic Devices and Circuit Theory by Robert L. Boylston and Louis Nestlesky. Okay, so you can follow this book and solve some of the problems based on this. Is there any questions you can ask? Else we will continue our discussion in the coming lectures.